three most common states of matter. We should know these by now, right? Somebody? Okay, solids, liquids, and gases. It'd be nice if that was a test question, but it's not. Of these, the state which has no definite shape and no definite volume, yeah, gases, the topic we'll be studying. Gases are so compressible because they consist mostly of, it's something that you don't think about very much. Good guesses. They're mostly empty space. There's actually nothing in between them. So I could take the air in this room and compress it down and probably put it inside a little Dixie cup. Okay? It's just, there's not much volume here. If you think about it, when I walk down the aisle, the hallway or whatever, it's pretty easy. I don't have a whole lot of resistance, right? When you walk through a swimming pool, if you're in a swimming pool and it's waist deep and you're trying to walk, can you go very fast? No, because you have to move all those particles out of the way, even though they're in the liquid state. So you are able to walk through gases so easily because it's mostly empty space. Yeah, you have little particles that hit you from time to time, but most of what you have is empty space, and that's why you have like propane tanks, those kinds of things. They compress a whole lot of gas and put it into a liquid. They can get that crushed down because they're removing the empty space. So it's just a different way of thinking about gases. They're easy to compress because it's mostly empty space. Okay, the four variables that are studied in this unit, and you need to know these. Volume, temperature, pressure, and the number of moles we have. Those are the four variables that you have to think about for almost every word problem that we have. Of course, Dalton's law that we just covered didn't have that, but it did have pressure. So a lot of times we might hold the volume constant and change temperature. Change temperature, or we might hold the pressure constant and change volume. We're going to change some and we're going to keep some the same. And so you have to be thinking about that all the time. So if I have a balloon and I've tied up the balloon, the volume at that point is, well, the number of molecules, the number of moles is going to always stay the same, right? Because I already tied the end up. I'm not going to add more to it. So that would always stay the same in a case like a balloon. And if I kept the pressure the same, since I've tied it off, the pressure in a balloon, the pressure inside the balloon is the same as the pressure outside the balloon. So the only two things that I might change if I put it in a freezer would be the temperature. And once the temperature changes, what's going to happen to the balloon if I put it in the freezer?
Freezes.
It's going to what?
Freeze. That's what the freezer is for, sir. It freezes it. So.
It's going to, actually the balloon will get smaller. Okay? And so we'll talk about all those things. You wouldn't think about that, but that's what's going to happen. Okay? Convert the following temperatures. You need to be able to do this. And the formula, the main formula you're going to use is Kelvins, K equals Celsius plus 273. And that's a very important one to know. It's in your blue periodic table, but it's written a little differently. So it's something you have to know. All the gas laws, when you're dealing with temperature, every single one of them has to be in kelvins. And the purpose of kelvins is to get rid of any negative temperatures. We can't have a negative temperature because if I'm dealing with math, how could I work a problem and come up with a negative volume? Robert, go to the store and get me negative 2 liters of soda. Wouldn't make any sense.
Why would you even go for a store for that?
Or Gavin, go change the pressure in the balloon to -2 atmospheres. There is no such thing. You can't have that. So they had to develop a temperature scale that did not have a negative. So absolute 0 degrees Kelvin, and actually they don't even put the degrees up there. 0 kelvins is called absolute 0. There is not a temperature colder than 0 degrees Kelvin. And we could get into how they developed it, and but basically that's the coldest it can ever get. It's absent of all energy. Okay, so kelvins, we have to do that. So using your calculator, if it's 25 degrees Celsius, how do we find kelvins? What are you going to do? Times 25 plus 273. What is that? Yes, 298. Somebody said that. Okay, so you're going to have to be able to fix that. MP stands for melting point. So it's saying the melting point of iron is 1,809 degrees Kelvin. So how would I change that? Well, I would just constantly use this. I know that 1809 kelvins equals Celsius plus 273. So how do I get that by itself?
Subtract.
All right, you're going to subtract. So 1,809 minus 273, 1536. It just goes back to it's not difficult to do, but write down the formula. Quit trying to do things in your head. Because some of you are going to make some simple mistakes like that. You're going to add to subtract. Okay, write down the formula. It doesn't take very long. 0 degrees Kelvin would be the same as what? Yes, negative. So same thing. If I said 0 equals C plus 273, well, 273 has to be a negative, doesn't it? So 0 degrees Kelvin, the coldest temperature ever, is going to be negative 273 degrees Celsius. And that's not even changing into Fahrenheit, which you're more familiar with. We will never deal with Fahrenheit. Fahrenheit is not a scientific scale for temperature. Okay, we don't deal with that. Most of the world doesn't deal with Fahrenheit. We're, again, one of the few countries. And then, so negative, the boiling point of xenon, the gas, is negative 108 Celsius. So again, K equals what? Negative 108 plus 273. Okay, good. 165. So everything, if it says temperature, everything has to be in kelvins. Everything, everything, everything. Okay, number 6. Something to think about that it becomes part of our kinetic molecular theory of gases coming up. Temperature is the measurement of the kinetic energy of the gas particles. Kinetic energy is how fast they're moving. So as it gets colder, they move slower. As it gets hotter, they move faster. So our temperature scales just measure how quickly, on average, the molecules move. The higher the temperature of a gas, therefore, the faster the particles are moving. Okay, so these are just things that it will help you conceptually as we start going through this unit, things that you really kind of need to remember. Pressure is defined as force per unit area on a surface. Next year, when you get into physics, you're going to be dealing with pressure and force, especially force. You're going to be dealing with that quite a bit. But that's what they're talking about. If you have a woman in high heels with a real tiny little, what do you want to call that, at the bottom, real small square heel, she steps on your foot, it's going to hurt really bad because all her weight is focused on a little tiny area. Okay? So the more force you have on a smaller area, the higher the pressure is going to be. Two instruments used to measure pressure. We talked about them briefly yesterday. Barometer. Close. Manometer. Yes. Okay. Barometer and manometer. One's closed end and one's open end is basically the difference. My understanding of those two.
Why? Why is it?
Because you use two different purposes. Gas pressure is caused by collisions between gas particles and any surface. So, kind of, what does that mean? Well, we talked about we said that temperature is the average kinetic energy, right? So it's the average speed at which the molecules move. So when you blow up a balloon, the thing that keeps that balloon inflated is the gas particles are moving and bouncing around inside the balloon, and they keep hitting the wall really fast. So as long as they keep hitting the wall, then that balloon's going to stay inflated. They don't stay there, but they're constantly moving. So if I put that balloon in a freezer, what's going to happen to those particles? Are they going to move faster or slower?
Slower.
They're going to move slower. If they move slower, are they going to hit the wall more often or less often?
No, they're going to be frozen.
Less. They're not going to hit the wall as fast, and they're going to hit it less often. So if you're not hitting the wall very often and you have something outside pushing in, what's going to happen to the balloon? It's going to get smaller. If you take that balloon and put it in boiling water and heat up those molecules inside, what's going to happen to the balloon? It's going to get bigger because they're moving faster, they're colliding with the wall more often. So you need to have that. That's what we're trying to get you to have a little background and understanding how pressure and temperature are related to each other. Okay? So you have to think about pressure being caused by gas particles on any surface. Okay, coming back to conversions, things that you love to do. So if I'm going to change atmospheres to millimeters of mercury, first off, we have to remember, we said 1 ATM equals 760 torr equals 760 mmHg, which equals 101.3 kPa. And again, we're not changing the actual pressure, we're changing the units by which we measure it. Like I said yesterday, a dollar bill and 10 dimes are the same amount of money. We just change the units by which we're counting. So anytime we do any conversions, guess what comes up? Our handy old T-chart. Whatever's given to us goes where? Top left. Okay? And then again, the units, whatever units up here, goes down here, no numbers. We want to change atmospheres into millimeters of mercury. And then you put the numbers in. So when I look up here, the number that's in front of an atmosphere is a 1. The number that's in front of my mmHg is 760. And then remember, we divide going down, multiply going up. That's pretty easy. 1 divided by 1 is 1 times 760 is 760. And I really could have figured that out just by looking at that 1 atmosphere equals 760, right? But I want to show you how we work them out. Okay, let's try this one right here. Oh, let's go to B. We'll stay in order. What's given to us in the upper left-hand corner. Units drop down. What are we trying to change it to? kPa. And then again, just go back to our factors, our conversion factors, and just put in whatever number it tells you. So it says that 760 torr is the same as 101.3 kPa. Put that in your calculator. Anybody else get that? Okay. 99.3 kPa. Told you conversions, we'll be doing them all year long. Hopefully it's going to help you next year. Hope you'll come in remembering that for physics. Okay, 2 more. Same thing, 100 kPa. So our kPa goes in the bottom, and we're trying to change it to millimeters of mercury. Okay, we put in our numbers. And someone had already finished that. What'd you have? Okay. 750 millimeters of mercury. And then last, you have 98.5 kPa. I'm going to change kPas into ATMs, atmospheres. So what do we have? 101.3 kPas is the same as 1 atmosphere. No, it's 0 point something. Got one more number, 2? Okay. trying to stay with significant figures. Okay, I think that's it. There's nothing on the back side.